Okay, so of course you know tomorrow we will all see each other in the various rooms. So quiz tomorrow, 1 o'clock, it's 75 minutes. I'm probably not going to release these notes until closer to the midterm, because then I can release them all at once. It's about 10 lectures in total, so it's 3 weeks, but I will release them at one time. It's just easier, and it makes more sense, and it aligns with your schedules. What we were talking about was friction. And so the whole idea that two objects, when they come into contact, there's going to be different levels of resistance to motion. So as I slide along that smooth table, it's very different than if I slide my hand along this surface here. And so as you're looking at this, you need to consider 3 different cases. So the 3 cases that we consider are no slip. If two objects in contact with each other do not move relative to one another, then the force of friction is less than mu static, coefficient of static friction, times the normal. The next case you consider is impending slip. Again, it's just like no slip in the sense that nothing's moving, but things are about to happen. In that case, the force of friction will equal mu sub s times n. And you're going to face a lot of problems where you have to sort of figure that out, and you have to identify whether it's impending or no slip. So just be aware of that as you're looking at these problems. Finally, of course, there's slip. In that case, you have the two objects moving relative to each other, and you have a different coefficient of friction. then your force of friction is going to be mu sub k, which is the coefficient of kinetic friction. So what's important here is to sort of recognize how to separate out these three different cases. And more importantly, how to identify when this happens, slip. We'll do an example, but not just quite yet. So here we have two masses, mass A and mass B, and I have chosen really good color schemes for this. A is on top. So the velocity of A relative to B, and hey, that relative velocity stuff is coming back now, is defined as the motion of A on B. If I look at A, I'm going to do something a little bit weird. And I know I saw on Piazza a lot of questions. What happens to the mass of the other object? You have a question, I think it's problem 2 in assignment 3, where you have two objects, one on top of each other, and how do you sort of deal with that? You transmit everything through normals. And so through Newton's third law, when you split an object like two boxes together and not consider the system, you're going to have a normal from B on A and a normal from A on B. I like teams, I really do. All right, so how you transmit the information or the forces associated with A on B is through a normal. And you'll notice if I add everything together, those normal forces disappear. So the normal BA is equal, opposite, and collinear with AB. I also have a force of friction from A on B and a B on A. And you'll notice that when I split those, I have the force of friction on top moving to the left and the force of friction on the bottom moving to the right. Friction opposes motion. The motion that I want to occur, velocity of A relative to B, is to the right. So the force of friction of A is going to be acting to the left. But if I split the system up, I have to consider that force of friction. I also will have another force of friction that opposes motion. And again, I kind of expect, and this will become more obvious as we go into momentum, that this box is going to try to move to the left. And if it does, the force of friction on C is again acting to the right. Normal from the floor, MBG. What you're asked to do a lot in this course is do free body diagrams. And so this is a nice one. It's a simple one in terms of the geometry. You'll have much more complex ones. But just breaking it up and solving everything becomes possible once you do this a couple times. Yeah. Just a reminder on springs. move that over here. XS. And just switch pens. XC. And so when we talk about these things, we often talk about stretching or compressing springs. So if delta in both of these cases is the same magnitude, delta is positive up, and I keep doing this. I'm going to make my life easier. This is y, this is x, and xs minus xo. And the reason why I want to write it as x is because I keep writing things like this as x. All right, so I have a relaxed spring. It has a length, when it is neither stretched nor compressed, of x naught. If I stretch it by magnitude delta, bring it up, I have delta, which is equal to x of the stretch minus x naught. And I have, force of the spring, because the spring, it's not the stretching that I do, it's the force in the spring. The spring wants to come back. So if the spring wants to come back to its unstretched position, the relaxed position, it will have a force that's acting in the opposite sense of its displacement. Same thing. Yeah, I could do it a different color. Here. Now, the magnitude of the force of both of those cases would be the same. I've compressed or stretched this spring by the same distance that ended up being delta. But the magnitudes are going to, or the directions, of course, are going to be different. So if you're wondering what exciting things await you in third, fourth year, well, right now we have a linear elastic spring. No surprise, we're going to also eventually see, not now, not in this course, nonlinear springs. A spring constant is defined as force over length, or in SI units, newtons over meters.
Sorry, I just had a question about the part just above. I don't understand why B is why we consider B moving to the right. Like for the friction, yeah, B moving to the left. So for the friction at B.
So A is being pulled. So eventually I will do the typical summer example, which is people on a raft, and they jump in this direction, but the raft moves in this direction. And one of the problems that this is in momentum, which will be in 2 weeks. But one of the things to remember is that I did not say velocity of A. This is velocity of A relative to B. The velocity of B relative to A will not be the same because it's much heavier, clearly, but it will be moving to the left. So that's why I start and get the friction forces acting to the right, because they oppose the motion of B. Yep. Springs. Sure. No, so sorry. In this particular problem you're talking about right here. So in this particular problem, I have defined at the very beginning velocity of A relative to B. If I were to solve a problem with this, I would say solve for velocity of B. So you're going to get velocity of B equals velocity of A plus velocity of B plus velocity of A relative to B equals velocity of A, whichever one I want.
Just so I understand that, from the like just velocity of A, is A moving relative to C? Like is A moving to the right?
No, so it's if I had two boxes, so I put this,
Is B the one moving?
A and B will move like this.
Yeah. So
A is up here, B is here, C is here.
I understand. So where's the velocity or the force being applied? Like,
We're not worried about that yet. This is not that problem. We'll get to that problem. I absolutely agree. That's going to be a great problem to do. Maybe we should do it now. Okay. So let's take a simpler case, or a case that has numbers and sort of relationships that we can look at. And there it is. I have here a crate of mass m resting on a dump truck. The coefficient of static friction between the crate and the bed of the truck is mu sub s equals 0.64. The truck must accelerate to the right to make the crate slide when the bed is in the position shown. Determine the smallest acceleration A for which the crate will begin to slide, expressed in terms of gravitational acceleration g. So one of the things you immediately notice is I haven't told you what mass is, I haven't told you anything about the truck. I have sort of given you theta, which is 30 degrees. Mu sub s. And one thing I should mention about mu sub k before I go away from that, mu sub k and mu sub s is always greater than mu sub k. Okay. So static friction is always a greater coefficient than kinetic friction. So one of the things that I have to do now is look at that crate. And if I look at that crate separately, I can say that under whatever conditions, I am setting this up in a problem where the velocity of the crate, the velocity of the truck are both equal because there's no slip. It's about to slip, but it's not slipping yet. And that's kind of important to remember. So mass times acceleration of the system makes it a lot easier. Go ahead.
whenever we see mu sub s, can we assume that it's mu sub s max?
So yeah, so mu sub s doesn't change. And I'll do a couple cases later where I look and calculate what the friction force is. You calculate the friction force and you calculate the maximum static friction that you can achieve. If your friction force is greater than the static friction, you have kinetic friction that you use. So it's a threshold value. That's all it is. But you can have much less than that. So that's the case of no slip, and then impending slip, which is this case right here we're considering. Okay. So, and I also, so the geometries get a lot easier here. All x, y. X, y is positive to the right, or x is right and up. Weight acting down, I've got the normal force, I've got force of friction, I've got mass times acceleration, everything is there. So the first thing I have to consider are all of the component forces acting in the x direction. And the forces acting in the x direction, there's the normal force right here, but it has to be acting in kind of the negative sense to fill that in. So I get negative n sine 30. And I have the force of friction, which is going to act in the normal direction, or in the positive x direction, or its component is going to act in the positive x direction. And that entire system will move with a mass times, or an acceleration of the truck and the box simultaneously. All right, so I got that with that. Next thing is now, one thing I'll often say is that the crate doesn't bounce, the crate doesn't move or go vertically. And so when you're dealing with y forces here, you only again have component of the normal force, you have component of the friction, but you also have the weight, which is acting vertically downwards. Mass times acceleration y is equal to 0 because the block isn't moving up or down. Now again, I'm not given mass, so I'm just leaving it as a variable. And it's reasonable to do so, and I probably should do exactly that with everything there. Remember, I don't know how much mass is. Okay. So I can calculate the normal force. It's equal to 0.8432 mass times gravity. If I substitute back in, so let's do this a little bit better. Then I can write this using my result from equation 2, substitute that into equation 1, and I can see right away that it doesn't matter what the mass of my object is. The crate doesn't play much of a role. And so that sort of is canceled, and you end up with the acceleration equal to 0.0458 g, or if you put in the numbers, 0.45 meters per second squared. Okay, so this is a nice problem. I mean, a couple of things I wanted to say is, first of all, velocity of the crate relative to the truck equals 0. So I know that because it's not slipping. If it were slipping, it becomes a much harder problem. Go ahead.
So at that acceleration, that means that the normal force, the x component would cancel out the forces trying to move down.
Yeah, so basically at that time, I would have friction forces which act up, and I'd have weight forces acting through the normal, weight and friction, the component of friction and the component of weight all together. So it's a subset of the weight. That total number is what's needed to hold everything in place. So normals, it's not as clear, but it's normals will hold in place. But if I were to introduce a tiny bit of acceleration beyond that, so I carried this out to 4 significant figures as 0.4491. If I go just a tiny bit above that, then I would see slip and everything would change, and I'd have a velocity of the crate relative to the truck. Wait, hold on. 1, 2, 1. I saw one of you three.
So essentially we're just calculating acceleration when friction is at maximum?
That's correct.
When we were answering this sort of question, it's asking what's the minimum acceleration for this to fall. We found the acceleration at like where it's equal. So would you just say acceleration greater than this quantity?
So what we're asked to find is the maximum acceleration where the truck, see, it says smallest, but what it means is the maximum acceleration where you still have no sliding, or the smallest acceleration where you will see the beginning of sliding.
So what I'm trying to say is that it would be A because the smallest acceleration. That value we calculated is it's still not sliding. So we just say
That's right.
greater than that.
Yeah, I mean, basically what I do typically, and I warn you about, is just say A is equal to this. It is the tripping point at which this will occur. It's a lot easier than, so say this is impending slip, and then that's it. Here we go. So you have a So the hard part in the last problem, the hard part sort of in that kind of hand-waving example that I gave at the very beginning, is not solving the problem. Solving the problem is pretty straightforward once you have the free body diagram. Getting a good free body diagram is crucial, and you're going to spend a lot of time on doing exactly that. So this is another example where here I have a crate which is attached to a spring. So that's going to introduce another force. Crate with mass m equals 45 kilos slides down an inclined plane with an initial speed of 8 meters per second. When it reaches the spring, it stretches a spring with spring, or reaches a spring with a spring constant of 100 newtons per meter. The spring is not compressed at this point, so it just is touching. Find the distance d that the particle travels, and remember a crate is a particle, from this point until it stops momentarily. And these problems will get a lot easier next week when you start doing work energy. Assume no friction between the particle and the plane. That plane is that blue bit, and that the spring has an unstretched length of 1.2 meters, and the angle theta is 25 degrees. So as is typical, you start out by writing all of the forces acting on this thing. I have the normal force. I've put it down here, but it's force of the spring. mg, which is acting vertically downward. And you'll notice that my coordinate system is set so that x is down the plane. Any questions back there? Up there. Okay, so if you're doing this, you then have to re-describe all of those components. So clearly this works out well in my favor because normal force and spring force are both acting aligned with my xy coordinates. So sum of forces in x, sum of forces in y. So here you have something different. So in the first example, in the first two examples, I had defined a coordinate system such that I had no y acceleration. But this time I kind of have something. So I have normal, because it's going to change in height, I have the force of the spring. I have the weight component, mass times acceleration in x. I have normal minus mg cos theta, mass times acceleration in y. Now, because I know this from the very beginning, the force of the spring is equal to kx minus L naught. So another advantage to defining this coordinate system the way they do, and again, this often comes up as a question, nothing deforms itself. Friction, or springs don't sort of wrap and warp and do all sorts of things. They go in and out linearly. So there's no weird sort of motion that occurs that you have to worry about or that we will trick you with. Instead, you're just going to have all of the force of the spring aligned with the x direction as defined in this particular case. All right, So I've put all of this down. Now I got to think about it a little bit. Ax is equal to x double dot. Good. Ay is equal to 0. It's not going to move up. It's just going to slide up and down. Everything's good. So my equations become a little bit easier. So now what I have are my governing equations. And I'm going to go through more detail in this example than I might otherwise, or when I do them later. This has 1 degree of freedom. And I can call that DOF. We have n is equal to mg cos theta. Okay, so that's not too bad. From the second equation. So now I have a governing equation, and it's based on substituting in for my force of the spring, substituting in for the weight component, substituting in for x double dot, which is m second derivative of x with respect to t. So this gives me acceleration as a function of position, not as a function of time. But what we want is velocity. So, fortunately, we spent a great deal of time on this. Oh, it gets more exciting. And that's your governing equation rewritten and getting rid of the mass terms. So except there. So So then I end up with this expression. This expression is just substituting in terms, recognizing that the terms on this side go with position, so just bring it over, VDV, but the only thing I haven't done is put the limits. Let me just see what color I have there. And the limit is 0 over here because I want to bring the crate to rest. So integrating this, I end up with this relationship. So in terms of the initial velocity, v naught squared, g d sine theta minus the spring constant times the distance squared is traveled over 2m. So if you carefully do everything that you need to do, you end up with mg over k sine theta plus or minus mk v naught squared plus mg squared sine squared sine theta to the 1/2. So it's a mess of equation. And it's a mess of an equation because I kept everything in variables all the way through. You would probably not, but it's kind of useful to see things. The other thing too, again, kind of useful for tomorrow, keep your units with your expressions. When you solve things, things will work out much better. So given all of my potential solutions, I get two results. One of them is a negative root, minus 3.816. We're engineers. That's not possible. On the other hand, that one is. And so the spring will compress by a distance of about 7.5 meters before reaching 0. The other thing to notice is that I don't care about the length of the spring. L naught doesn't play a role in this problem at all. L naught doesn't appear at the end. Everything else kind of does. Now, another quick sort of check you can do after the fact is put in all your units and make sure that all of the terms actually make sense. If you do that, that's actually a pretty quick way to catch an error that you might have made. We do the same thing, and if you do it in a consistent way, you can always solve all of these problems no matter what you face. So it's really important that you don't just sort of throw everything down on the piece of paper. So one. Okay, so when you're solving these things, first of all, look at what you have. Circle the numbers down, make sure you have everything down. Sketch the free body diagram. Please, please, please don't just sort of look at it and say, oh yeah, I know everything is there. Sketching takes seconds. Put a box, put things on. Don't put a dot, put a box so you can see all of your forces. Create a model of the problem, and then you set your strategy. Now, one of the things that will come out in the next week, this problem, for example, is a lot easier to solve as an energy problem. There are different ways of solving all of these problems. This is sort of the foundational way. In the next 2 weeks, what we'll talk about are ways to speed up the solution, but you still have to draw the free body diagram, still have to set up the system. So make sure you understand how you're doing this. After you have your free body diagrams, and you'll notice, by the way, I kind of sort of skipped over it, but I will use FBD a lot because I'm lazy and I don't want to write free body diagram every time. So that's just a consistent notation. So you're going to then break Newton's second law into its x and y coordinates, r theta, and t, you can guess where that's going, but into components from that FBD, the free body diagram that you just drew. So the free body diagram is the most important part of this. Once you have a good free body diagram, once you've considered all possible forces, you're set. But if you miss one, your equations of motion will be wrong. Then you take in the kinematics. So for example, on this problem, we went through and we looked at the kinematics at the end when we derived this relationship right here. So we recognize in this case that you have a term that goes as v dv dx. One of the reasons why I like Piazza and other sort of online forums, and I do encourage, and one of the things we haven't been able to do, is have you discuss your solutions. And so to think really hard about why you're getting everything there. So the next step, after you do this, work with the equations to get your solution. Once you have a good free body diagram, you can easily write the equations of motion. The hardest part really is the free body diagram. And really, it's important to know what your dimensions, your units, your values are, so that when you look at a number, you don't come back and say the acceleration is 3 kilograms per second.